Welcome back to the deep dive. Today, we are going to try and fundamentally shift where you focus your anxiety about climate change.
That sounds promising. Or maybe just a different flavor of ominous.
A little bit of both, honestly. I mean, look, usually when we talk about climate risk in coastal cities, everyone looks up. We look at the atmosphere, we look at carbon, the melting ice sheets.
The narrative is always the water is coming up.
Exactly.
Yeah.
And, that's not wrong. The water's rising, but it's only half the equation.
It is absolutely only half of it.
Today, we're looking at the massive, sort of invisible other half. While the water is rising, the ground beneath the feet of nearly 500 million people is, well, it's collapsing, it's sinking.
And in many of the most critical places, it's sinking significantly faster than the sea is rising. We're digging into a landmark study from 2026 by Elo Owenhan and a huge team of researchers. It's called Global Subsidence of River Deltas, and it's honestly one of the most comprehensive planetary health checks I've ever seen.
It's massive. They didn't just, spot check a few beaches. They analyzed 40 global river deltas with high-resolution satellite radar. We're talking the Nile, the Mississippi, the Mekong, the Ganges.
The arteries of civilization, basically.
Yeah. And our mission for this deep dive is to understand this thing called VLM, or vertical land motion.
It sounds a bit dry, VLM,
Yeah.
but it's effectively the difference between a city surviving this century or becoming an underwater ruin. We need to get into why the ground is giving way, what the human fingerprints are, and here's the twist, why this might actually be the good news part of the climate crisis.
I was so skeptical when I saw good news in the notes, but after digging in, I actually see it.
Yeah.
But let's set the stage. Why focus on deltas? Geographically, they're tiny.
They are. They're only about 1% of the Earth's land area, but that 1% is incredibly potent. You've got, 350 to 500 million people living there?
Wow, so that's like 4 to 6% of the entire human population.
Squeezed into that tiny sliver of land. So these aren't just remote wetlands.
No, these are economic engines.
Massive ones. They're the world's breadbaskets, huge port cities, mega cities. And because they're naturally low-lying, they're basically just piles of mud at sea level, they are on the absolute front lines of climate risk. But what this study shows is that we've been calculating that risk with one eye closed.
Okay, so let's open that other eye. The studies are making these huge claims. They didn't just send people out with rulers.
No, the scale's way too big for that. They used a technology called INSAR, that's interferometric synthetic aperture radar.
Which is a mouthful. It's basically space radar, isn't it?
Precisely. Satellites bounce radar signals off the ground to measure its surface level. And the precision is just mind-blowing. We're talking millimeter-level accuracy.
Yellow-meters from space.
Yeah. They crunch data from 2014 to 2023, a whole decade. So you can see the land breathing almost. You can detect these tiny drops in elevation that are invisible until, it's way too late.
And when you put that sinking data on top of the rising ocean data, you get what the study calls the double burden.
That's the key concept. You've got the global sea level rise, which is the ocean expanding from heat and meltwater. That's one thing. But then you have the local land sinking, the subsidence, to get the real risk, what they call relative sea level rise, or RSLR. You have to add them together.
So if the ocean comes up 3 millimeters and your land sinks 5 millimeters, the water just got 8 millimeters closer to your front door.
You're running up a down escalator. And the findings are, they're startling. In 18 of the 40 deltas they studied, the land is sinking faster than the sea is rising.
That just seems like such a crucial point. We spend all this energy on the global sea level rise, which is, 3 or 4 millimeters a year. But in almost half these places, the ground is dropping out from under them even faster.
Much faster in some cases. The study points to the Chao Phraya in Thailand, the Brantis in Indonesia, the Yellow River in China. These places are sinking at more than twice the rate of global sea level rise.
So hypothetically, even if we magically solved climate change tomorrow, froze the ice caps, oceans stopped rising, these cities would still be drowning.
They'd still be sinking themselves into the water. That is the terrifying reality. And we aren't talking about empty marshes. The study defines a danger zone, places where sinking is outpacing sea rise. About 236 million people live there.
The stat that really got me was about the most vulnerable, I think it was. If you look at people living really low, below 1 meter of elevation, something like 84% of them are in these rapidly sinking areas.
Yeah, it's an inequality crisis as much as it's a geological one. But to fix it, you have to know why it's happening. Is this just nature?
By the detective work. Because, mud settles, that's normal. But the rates they found are way too high for that. So they looked at 3 main human suspects: groundwater pumping, dams blocking sediment, and just the weight of our cities.
Exactly, but it gets tricky because you can't just say add a million people, get a centimeter of sinking. The relationships are messy, they're all tangled up.
So they brought in the heavy artillery, the algorithms.
They did. They used machine learning, specifically a random forest model, to untangle all these different variables.
Random forest. Sounds like a new craft brewery.
It does, but it's actually a really powerful way to figure out what's really driving the bus. When you have messy interacting data, a simple line graph just won't work. A random forest model, it basically builds thousands of little decision trees to find the real patterns in the noise.
And the algorithm pointed a finger at one main culprit,
Groundwater extraction.
the big one. And I want to make sure we really get the physics here, because it's not just that the water is gone, it's about the Earth's structure.
Right. You have to picture what's under these cities, these layers of sand and clay aquifers.
Mm.
Think of them as a saturated sponge. When it's full of water, the water itself is pushing back. It's holding everything up.
It has structural integrity.
Exactly. But then we need water for farms, for industry, for drinking. So we stick a straw in the ground and we pump it out.
And the support structure just vanishes.
Yeah.
The sponge collapses under the weight from above. The ground literally shrinks,
And here's the really scary part. Often that's inelastic.
meaning you can't just pump water back in and reinflate it.
Not really. Once those clay layers pancake, they stay pancaked. That storage capacity is gone forever. The elevation is lost. The study points to the Mekong, the Ganges Brahmaputra, and the Rhine Meuse as places where this is the dominant problem. We are literally drinking the ground we stand on.
We are, but it's not the only way we're doing this to ourselves. The second culprit is what you called sediment starvation.
Right. And this one is a bit more counterintuitive. We tend to think of rivers as just water pipes.
But they're really conveyor belts for dirt.
They are. A natural, healthy delta is always rebuilding itself. The river carries silt and sand downstream, and when it hits the ocean, it slows down and drops that sediment, building new land. It's a regenerative cycle. It counteracts the natural sinking.
But we put a stop to that conveyor belt.
We've broken it. We build these massive dams upstream for power or irrigation, and they trap all that precious sediment hundreds of miles away. The water that gets to the delta is hungry water. It has nothing left to give.
So the delta sinks a little every year from compaction, but there's no new dirt coming in to top it up.
You got it. And the study shows this is a huge deal for the Mississippi, the Amazon, the Rio Grande. The Mississippi Delta has lost, 5,000 square kilometers of land since 1932.
That's an area larger than the state of Rhode Island.
It's a staggering amount of land, and a huge part of that is because we've built levees to control the river. We've turned it into a chute. The sediment doesn't spill out into the wetlands anymore. It just shoots straight out into the deep Gulf of Mexico and is lost forever.
So we solved one problem, flooding, but we created a much bigger sinking problem. And then there's a third suspect, which is just brute force, urban expansion.
The sheer weight of concrete, steel, asphalt, millions of people. We forget how heavy cities are. In places like the Siliwang Delta, that's where Jakarta is, the city is physically compressing the soft ground beneath it.
And I'm guessing these three things, pumping water, blocking sediment, building cities, they all feed each other.
Oh, absolutely. That's why the simple math failed. A city grows, it gets heavier. That same growing population needs more water, so they pump more groundwater, which weakens the very soil the heavier city is sitting on. It's a compounding feedback loop.
Okay, that paints a grim picture. But the study goes a step further and maps this onto geopolitics, this impact matrix you mentioned.
I love this part because it moves us from pure geology to actual policy. They plotted the 40 deltas on two axes. One is risk. How fast is the relative sea level rising?
And the other is readiness, using something called the ND Gain Index. What is that exactly?
ND Gain is the Notre Dame Global Adaptation Initiative. It basically measures a country's vulnerability to climate change versus its readiness to adapt. Is your government stable? Is your economy strong enough? Do you have the tools to handle a crisis?
But do you have the money in the organization to actually fix it?
Basically, yeah. And this creates 4 quadrants, and it really lays bare the inequality of this whole crisis. The worst quadrant is what they call the unprepared divers.
High risk, low readiness. The worst place to be.
And it's the most crowded room. 26 of the 40 deltas are in there. We're talking about the Mekong, the Ganges Brahmaputra, the Nile.
The Nile example in the paper was it was heartbreaking. It showed how in the 20th century, the Nile was a latent threat. Relative sea level rise was maybe 1 millimeter a year.
Oh.
Manageable.
And now it's surged to over 10 millimeters per year. The Aswan High Dam cut off the sediment. Population growth drove massive groundwater pumping. So now you have a delta sinking fast in a region that's struggling. They just don't have the billions of dollars to fight back.
So they're taking the most damage with the fewest tools. Then you've got Quadrant 2, rising ready. High risk, but high readiness.
These are the wealthy nations.
Mhm.
The Mississippi in the U.S., the Rhine Meuse in the Netherlands, the Yellow River in China. They have the same sinking problem, but theoretically, they have the money to throw at it.
But the paper makes a really sharp point that just because you can adapt doesn't mean you do.
The Mississippi is the perfect example of that. America is the wealthiest nation in history, yet its largest delta is hemorrhaging land. We have the money, but not the political will or the coherent strategy. We've prioritized shipping and oil over land building,
Compare that to the Dutch with the Rhine-Meuse Delta.
the gold standard.
Mm.
The Dutch have essentially turned their country into a high-tech survival machine. They use hard engineering, but they also use nature-based solutions. They give the river room to move. They prove that being rising ready is possible, but it takes this massive, unified national effort.
And then the safe havens. Low risk, high readiness. I'm guessing that's a pretty small club.
A very exclusive club. Only 2 deltas out of 40 made the cut. The Fraser in Canada and the Rioni in Georgia.
The country of Georgia.
Correct. And even there, safe is a relative term. The Rioni as a whole has some weird local dynamics that are helping it, but specific cities like Poti are still sinking fast. So even in a safe haven, you can still be in deep trouble.
So if we zoom out, the ground is sinking, often faster than the sea is rising. The poorest nations are getting hit the hardest, and even rich nations are failing to manage it. It feels like we're just losing.
It does feel that way. But remember that twist I promised? This is where we get to the silver lining.
I'm so ready for it. How is any of this good news?
The sinking itself isn't good, but the cause of the sinking creates an incredible opportunity. Think about the difference between global sea level rise and subsidence.
Okay.
Global sea level rise is driven by global carbon emissions. To stop it, you need the whole world to act. China, the US, India, everyone. It's a huge, slow, diplomatic ship to turn.
Right. A city council can't pass a law to refreeze the Arctic. The atmosphere doesn't care about borders.
Exactly. But subsidence, that's a local problem. It's caused by local decisions. The decision to pump groundwater in Bangkok, the decision to dam a river in Egypt, the decision to pave over wetlands in Jakarta.
Which means it can be fixed by local decisions.
Precisely. We don't need a global treaty to stop Tokyo from sinking. We just need Tokyo to change its water management policy. And we know this works. The study calls it a socio-technical imperative.
So we have to stop just thinking about building higher walls. We have to actually stop the ground from moving in the first place.
Yes. If you regulate groundwater use, if you do managed aquifer recharge, which is basically pumping water back into the ground, and if you build sediment diversions, you can slow or even stop the sinking.
And you could do that much faster than fixing the global climate.
Much, much faster. Climate action takes decades to show results because of the lag in the system. But subsidence control can show results in just a few years.
That's a proof of that.
Oh, absolutely. Tokyo is the classic case. In the mid-20th century, it was sinking like a stone, centimeters a year. Then they passed strict groundwater regulations, switched to surface water.
And what happened?
The sinking pretty much stopped. It flatlined. Shanghai has done similar things. It's a problem with a proven, executable solution. We don't need to invent some magical new technology. We just need to manage our resources better.
That is a huge shift in perspective. It takes the problem from we are helpless victims of a global crisis to we are mismanaging our local environment and we can choose to stop.
Exactly. It puts the agency back into local hands. If we ignore the sinking ground, the rising sea becomes an impossible problem to solve. You can't build a wall high enough if its foundation is dropping. But if we stabilize the ground, we buy ourselves a fighting chance. We buy time.
It's like we've been fighting a war on one front, carbon, while ignoring this other front where we could actually score some quick wins.
That's the takeaway. We have to do both, of course. But the ground beneath our feet is the immediate battle. And I want to leave you with one final thought from the data that really drives this home.
Go for it.
When you look at the total area of all the sinking deltas, it just feels overwhelming, like it's everywhere. But the data shows that 57% of that sinking area is concentrated in just 7 massive river systems.
Wait, hold on. Just 7.
Just 7. The Ganges, the Nile, the Mississippi, the Mekong, the Yangtze, the Amazon, and the Irrawaddy.
That actually makes the problem sound incredibly solvable.
Doesn't it? Instead of fixing the whole world at once, we have 7 specific targets. 7 places where smarter policy on water and sediment could save millions of lives and protect huge parts of our global food supply.
It turns an infinite problem into a focused to-do list.
A very high-stakes to-do list, but a manageable one.
I like that. It's not everywhere, it's right there. And we know what needs to be done.
We just have to decide to do it.
Well, next time you're near a coast or looking at a map, take a second to think about what's happening underneath it all. It's not just about the water coming up, it's about the ground we stand on. And keeping our feet on solid ground, apparently, takes a little more work than we thought. Thanks for joining us on The Dive.
Thanks for having me.